Hello, I'm Sue Nelson, and this week's Planet Earth podcast is from Gloucester Airport, and I'm beside a very special scientific plane. It's a little bit windy, but fortunately the weather is good enough for me to go flying in it. But what about the weather in space?
It can disrupt technological systems, modern technology. Technologies such as aircraft, satellites, even ground-based technology, actually including power grids.
More on that story later. Gloucester Airport, or Staverton as it's known to locals, is a typical small regional airport. There are several training schools here, quite a few Cessnas and a few private jets. But it's the Dornier remote sensing aircraft that has brought me here today. And I'm with Carl Joseph, who's the Flight Operations Manager and Pilot for the Natural Environment Research Council Airborne Research and Survey Facility. Carl, what makes this plane so special? What has turned it from a Dornier 228 into a remote sensing aircraft?
What makes this aeroplane special is that it was actually manufactured as a scientific platform. So instead of really actually fitting the cabin area with seats, we've got a 2-metre hole or 2.1 metre hole in the floor that allows us to put a load of scientific instruments in, and they have a clear view down to the ground, so it makes it an excellent scientific platform.
Now, there's an aircraft, that's a helicopter just taking off beside us. Describe this plane for me. I mean, I can say it's a gloriously patriotic colour of red, white and blue, but it's got a couple of propellers, but I think we need a bit more technical terms than that.
Yeah. It's a twin turbo, what we call a twin turboprop aircraft, which allows us to fly fairly high. The service ceiling on this aeroplane is about 25,000 feet. However, for science, we tend to restrict that altitude to about 15 and a maximum 20,000 feet. Also, the range of this aeroplane is absolutely superb because it allows us to fly pretty much all over Europe and further afield than that. Additionally, the aeroplane is non-pressurised, so it allows us to fit novel instruments to the aircraft structure, and we don't have to worry about pressurisation or anything like that.
Well, one of the crew members is James Johnson, who's an instrument operator. What instruments do you actually operate on board this plane?
Okay, well, the instruments that we're going to operate, which is the main core suite that we have on board, are the LiDAR, the light detection and ranging system, and the Eagle and Hawk sensors, which are hyperspectral systems looking at shortwave infrared and very near infrared.
Well, let's go on board the plane briefly before we take off to have a look at this. A few full small steps, rather like a sort of roped gangplank onto the ship. Let's get inside now. Oh, it's quite narrow, isn't it? It's less than a couple of metres across, and we're both having to stoop. So we've got some black boxes. Which is which?
The instrument down the end there, the sensor that you can see there, that is the LiDAR, which basically...
The silver box.
The silver box at the end there, that's the LiDAR. That will produce a digital elevation model of the ground. So it's a laser that fires down to the ground, and we pick up the return and can actually map the ground and see the contours of the ground.
And what are you actually looking for when using a LiDAR?
What we're actually doing, we mainly use that as a base model to lay other information on. We can overlay the hyperspectral data on top of that, so you get a 3D image of the ground. You can also use it for intensity, so looking at the structure of a canopy in a forest or something like that.
So you're specifically interested in the elevation of the ground at any specific point?
Yes, you could. I suppose you could put it that way, yes, indeed.
And what would that information be used for?
I suppose that they would use that information for looking at various different things such as erosion. You can see that the difference that something has moved, for example, a glacier. You can actually see from 6 months ago, if we've surveyed a glacier in Iceland or Greenland, you can then go back and do another LiDAR survey, and you can see how that has moved and how it's changed, its features have changed over a period of time.
Now, in front of the silver box, the LiDAR, we've got a bigger, sort of an old-fashioned 1990s stereo, really, looking, isn't it? Like a stack of black boxes.
Yes, that is the hyperspectral system. So what that does is looks at the ground again, and it looks at it in the shortwave infrared and the very near infrared bands. So it's not looking at what you can see with your eyes specifically. It's looking at, for example, yes, that's a green leaf, but what kind of green is it? Is it an oak tree? Is it a beech or something like that?
That can tell the difference.
Yeah, you can look at stuff like that.
Good grief. Now, the pilot, Carl, said that there's a hole in the middle of the aircraft, but I can't actually see that hole. Is that because this instrument is placed over the hole?
Yes, all of these instruments are placed over the trench that is in the middle of the aircraft. You will never be able to see down to the ground from inside the plane for safety reasons. There's no danger of anything or anybody falling out.
Well, I'm very glad to hear that, because we're about to take off to do a short flight. This will be a calibration flight,
Yes,
is that right?
Yeah, that's correct. What we're actually doing here is we are checking the instrumentation, checking it is working. The data that we collect will be sent to our processing department, and they will tell us whether there's been any shift in the sensor heads and that all of the instruments are functioning correctly.
Well, I'll go and tell the pilot, Carl Joseph, then that we're ready to take off. And it may be a sunny but windy day where I am now in Gloucester Airport, but anyone who's suffered a rainy, cold, so-called barbecue summer will know how difficult it is to predict the British weather. So how about predicting the weather in space? Richard Hollingham is just back from a space insurance conference in Italy, where space weather forecasting was a hot topic among those responsible for operating satellites and insuring spacecraft.
I'm walking across a park in the centre of Rome, and, well, the weather is lovely. Clear blue sky, slight wispy clouds, a light breeze, and as you can hear, all the birds singing in the background, and occasionally you'll hear some exotic birds too from the nearby zoological gardens. But that's only half the story. Richard Horne is here from the British Antarctic Survey. What's going on then beyond the atmosphere, beyond that plane we can see in the sky?
Well, we're familiar with the terrestrial weather, but actually out in space we also have weather, so to speak. We call it space weather. It really is driven by variations on the sun. We have the material flowing off of the sun, which we call the solar wind, that flows towards the Earth, and that can disrupt the systems at the Earth. It can disrupt technological systems, modern technology. Technologies such as aircraft, satellites, even ground-based technology, actually including power grids.
Now, David Wade, you're from Atrium Insurance. Satellites, that's what you're worried about because you insure them. What impact can this weather, this stream of charged particles from the sun have?
Can have a number of impacts. One of the most obvious ones to think of would be a loss of power. The sun pours out some protons. Those protons hit the satellite solar arrays, and the solar arrays are degraded. So over time you could actually see the satellite's power levels degrade, and therefore the functionality of the satellite would be also degraded. But you can also get charging, where different parts of the satellite charge up at different rates, and an arc forms between the two differently charged parts. And when that arc discharges, it could cause damage to the satellite.
And what sort of impact would that have on us?
Well, typical impacts could be the loss of communication services, so maybe your satellite TV gets knocked out, but other aspects such as the GPS system, the navigation system that we've all become so used to these days. You know, we think of it as directing us when we're driving our cars, but it has much wider uses than that. Financial transactions, mobile phone towers, the coordination of those cellular towers for mobile phone calls, all of those are governed by the timing signals that we get from the GPS system.
So potentially you could lose almost all communications if you knocked out, for example, GPS.
Absolutely. GPS is a constellation of satellites, so there's numerous satellites up there. So chances are you may not knock all of them out together, but you could certainly get a degraded service. And that could also be a degraded navigation service. You could see the impact on flights which have to be rediverted, or shipping which may not be able to dock at a particular time. They may have to wait until a geomagnetic storm subsides before a ship can dock, for example.
Now, are we talking here, Richard, about a hypothetical situation, or could this really happen?
No, there are examples where this has really happened in the past. If we go back to 2003, there was a very big magnetic storm at the Earth, and we had something like 47 satellites were reporting anomalies, that's malfunctions, things which go wrong in spacecraft. One satellite was a total loss. That was a scientific satellite, it was a Japanese one. It cost $640 million, that's a lot of money. The fact that we've had very large magnetic storms like this in the past means that we can have them again. And indeed, over the next few years, we are expecting a number of magnetic storms to increase. So, for example, we know that the Sun has an 11-year solar cycle, and we usually measure that by the number of sunspots. But in terms of the magnetic storms, we can also measure that at the Earth, and we measure that by the changes in the Earth's magnetic field, variations in the magnetic field. And we know that the number of storms is going to increase typically 1 to 2 years after the solar maximum, the maximum of the sunspot number. So over the next 3 to 4 years, there's going to be a period of increasing risk when storms occur, and those storms damage satellites and a variety of other infrastructure.
Now, you say risk. Can you see those coming then? That these events that are going to have potentially that sort of impact?
It's a very difficult thing to do. We can see some precursors, we can see some indications that the Sun is going to emit large bursts of plasma material away from the Sun. But at the moment, it's very unreliable. Trying to forecast when the Sun is going to do that and when they're going to hit the Earth is very unreliable. The best we can do really is to take information from a particular spacecraft near the L1 position, that's between the Sun and the Earth. The spacecraft is called ACE, and it measures the magnetic field flowing off of the Sun. And by those measurements, we can then combine that with computer models, and we can try and make a forecast of what's going to happen at the Earth.
And how much difference would it make to get an accurate figure, David?
Certainly having that information would be very useful. In terms of insurance of satellites, it's not something that we can ask a satellite operator to turn off the television channels, but certainly for aspects on life and or on the ground, it would be tremendously useful. Certain functions could be prepared in advance, certain financial transactions that are essential could be prepared in advance. Maybe alternative methods could be used, and if that warning is there, an alternative method could be used for the time of the geomagnetic storm.
What would you like to do then, Richard?
Well, let me tell you what we are trying to do. We're just starting a new project. It's called Spacecast, and we're going to take data from satellites. We're going to run that through our models, and we're going to try and generate a forecasting capability. And we're going to issue warnings and alerts for periods of high risk. And we want to try and make contact with insurance companies, satellite operators, satellite designers as well, so that we can try and help them minimize the risk. For example, if we can be more involved with satellite operators and we can issue warnings and alerts to them for periods of high risk, then we can help them protect their spacecraft. So it's a good interest for them, it's an interest for the insurance companies, because they want to be reassured that the operators are taking all measures possible to try and reduce the risk of damage and loss.
Now, you're both dealing with risk here. How worried should we be?
The real big problem, the real question is into the future, would there be some major superstorm? Would there be some kind of disaster? Back in 1859, we had a very, very large storm called the Carrington Storm. It's the largest one we have on record. Something like that has never happened in the spacecraft era. If it did, the consequences could be enormous. It has been estimated by some scientists that the impact of that, the financial impact, could be as high as something like $30 billion. That's a huge amount of money.
Richard Horne from the British Antarctic Survey, ending Richard Hollingham's report from Rome. You're listening to the Planet Earth podcast, airborne on board a twin-turbo prop plane, a Dornier remote sensing aircraft.
Sierra Alpha, contact Fiber 125.250.
Right, just going to go open the door.
125.250, Alpha, bye. Maybe historic price radar, pass message.
Navy Historics, pair of chipmunks, total 4 POB, Kemble to North Weald. Currently about 3 miles to the southeast of Kemble, climbing initially to 2,000 feet on the Cotswold 1022. Basic service, please, and we are squawker cable.
Well, we're several thousand feet above southwest England now, and I'm sat next to James, the instrument operator. Rather unusually for a plane, we're sat with our backs to the pilot instead of facing the direction of travel, which I must admit, even for somebody like me who loves flying, is not that great on the stomach.
That's right, I know what you mean. When I first started to fly on the aircraft, I noticed it didn't feel so good either. But we actually do this for a reason, that we now have the whole cabin for us to move around in.
That's true. In front of us is the end of the aircraft. We're looking down it at the instruments.
Yes.
And you've got 6 computer screens in front of you, as well as a sort of more mobile, flexible one in front of me, where we can see the ground beneath us that's being viewed from the instrument at the centre of the plane that's looking now through a hole in the bottom of the plane.
Exactly right, yes. So basically what we have here is the webcam. So this is a continuous reel of all of the ground that we're flying over. And then the LiDAR, we have the LiDAR controls, as mentioned earlier, which is a laser that's firing to the ground and taking an elevation model of everything that we are flying over. On these screens here, the 2 that we're really interested in are these 2 screens, which one of them is the Eagle, which is one of the hyperspectral systems on board, and the Hawk. And as you can see, as we're going across the ground, it is looking at what we are flying over. These spectral profiles that you have here,
they're changing as we're moving, so the peaks and troughs of the graph, effectively, in bright red in this case, are sort of alternating and moving, sometimes higher, sometimes lower.
What that is actually looking at is, as the graph increases, it's an area of light that we're going over. So it could be a lighter field, it could be, for example, an oilseed rape field would basically saturate the screen, and that data would actually not be any good. So we have to set the instruments up with regard to the frame rate that the instrument is running at and the integration time, just like a camera basically. And then that information, as you can see here, we're flying over an area with sunlight over it, so this is starting to show quite a bit of movement across the spectral profile and increasing to the upper limits of the scale.
On average, how long are your flights, not just for calibration, but for the actual remote sensing of particular areas in themselves?
We're now doing surveys that are sort of 4 or 5 hours at a time, and that's a pretty standard survey for us. Then come back, land, and then deal with the data on the ground.
Okay, do you want to close the door, James?
Closing the door.
Flaps coming up, Dave.
We're heading back down now, just as well, because it's getting bumpier, and I'm beginning to feel a little the worse for wear. We've landed. Oh,
You okay?
yes. Oh, all the air smells. Feels fresh and sweet now.
How was that?
Much bumpier than I expected. It did make me feel sick. Yeah, a little bit. Yeah. Oh.
We were quite low. That's why.
Yeah.
It's probably more bouncy today than normal.
All right.
Thermal activity as well there.
Sorry, I'm still feeling a little bit sick after that.
Take a few minutes if you want.
That's all right. David Davis, you're electronics officer for the Natural Environment Research Council scientific plane here. Was that par for the course, that bumpy ride? Because if so, how on earth do you do several hours at a time?
Sometimes it can be very bumpy, sometimes it's very smooth. Today was quite a bumpy day, and we can often spend up to 5 hours turning backwards and forwards in those conditions. So to actually work in the back of the aeroplane, you've got to be made of pretty stern stuff.
In this case, this calibration was done locally, but this plane actually operates, as was alluded to earlier with pilot Carl Joseph, on a sort of global scale, doesn't it?
Absolutely. I mean, we've flown the aircraft around the world. We've been to Australia, South America. We work a lot in Greenland and Iceland and far-flung places like Svalbard, which is all the way up in 79 North. The aircraft's very useful. It can operate from gravel runways and short airstrips, so we can make use of the outback type environment.
Couldn't satellites do this kind of work?
Well, the satellites can do a lot of it. We fill in the gap between the ground measurements and the satellites. Our data is generally more finite than the satellite data. The resolutions are better both spatially and spectrally, which means that the scientists using the data can absolutely pinpoint what they're looking for and use it in conjunction with the satellite data as well. We also collect a variety of atmospheric data for aerosol and chemistry, and that will be disseminated to a different set of scientists. There's a lot of work completed post-flight by our data node in Plymouth Marine Laboratory to process the data to a standard where the scientists can use.
So it's not just land use, glaciers, climate change, it can be oceans as well?
Yeah, we can cover everything from marine, archaeology, geology, ecology and anything in between. So if the scientists can think of a good project for it and put their application in, providing their science is graded to a high enough standard, we will fly it.
David Davis, thank you very much indeed. Well, that's it from me at Gloucester Airport. You can see photos of the plane on our Facebook page, and you can check out the latest news from the natural world on Planet Earth Online. I'm Sue Nelson, and you've been listening to the Planet Earth podcast, both above and below Gloucester Airport.